In the continuous time signal, you have the t, you can write the EAT. In the discrete time, you have the k, you can write the EAK, or you can write the EK. Useful continuous time functions, you have the step, that means less than the t less than the 0 is equal to 0, and bigger than t equal to the 0 is equal to 1. Ramp t less than 0 equal to the 0, and bigger than this is the continuum by slope 1. Dirac delta, that means they have a value on t equal to the 0, that means Dirac t minus t self, they have a value on the Dirac t self is equal to alpha. And if you continue the Dirac, the name is Dirac of the comb, that t is equal to 1. That means Dirac will be continuous in the real axis of the t. You can write the properties of the Dirac t. If will be 0 only t is equal to the 1, it becomes finity. Or you can write the integration minus finity to finity of the Dirac t is equal to 1, because only Dirac they have a value is here, minus finity here to plus finity, only they have a value only the 1. For any function of e minus finity to finity, et Dirac t minus t 0, they have a value of the, here is e t0, or the comb will become sum of the k equal to minus finity to finity Dirac t minus kt. And if you give the value of the k, they start to go ahead, the name is the comb of the Dirac t. In the discrete time step, you have the sample time of the t less than 0 and the sample time of the t bigger than 0. For the ramp, the same thing. For the Dirac only, they have a value on the is equal to t equal to the 0, is the Dirac will be 1, and the comb is n equal to 4. You have the 4 sample of the Dirac k. Sorry, here is not the t, is a k equal to 0. The property is the Dirac k will be 1, n equal to 0, this is normal. If n or the k equal to 0 or n equal to 0, Dirac k will be 1. Or the before you said integration, here become the sum of the k equal to minus finity to finity EK Dirac k minus k0 become EK0. That means any signals multiplied by the Dirac k minus k0 is here, k0 here, the value will be here, become EK0, because here is a 1. Any signal multiplied by Dirac k minus k0 will be the value of the EK0, or the signal in this k0. The comb will be Dirac n minus kn, and the k equal to minus finity to finity. By convention, if E has a discontinuity in the k0ts, then ESAK0 take the value after the discontinuity. If the E has the impulse of the weight A in k0t, then EAKT take the value of the ATS. Using this convention in the Dirac and the step and the ramp, you will see that Dirac is a function of the Dirac k, a step k is a function of a step k, and the ramp of the S become a function about the ramp of the k. How can I use this thing? By conventional rules, Dirac delta, they have a value of the 1. In the discrete times, Dirac k, they have a value of the sample about the 1 divided by Ts Dirac k. For the step sample k become a step k. And for the ramp sample k become Ts ramp k. And if I summarize of this, Dirac sample k, that means if you have a Dirac, if I take the sample of this, sample of the Dirac k will be 1 Ts Dirac k. A step doesn't change. For the ramp sample k become ramp about the kts or Ts ramp k. This is the sum of this rule that we learned. Now we go to Z transform. Z transform you should keep in the mind in the unilateral Z transform of the discrete signal of the EAK, any signal, EAK, AAK, TAK, any signals can be defined by the sum of the K from 0 to infinity EAK Z minus K with region of convergence of the between R0 and R small r and big R. This region convergence I will discuss later. Unilateral start by K equal to 0 to infinity. Bilateral here is a K start by minus infinity to infinity. Okay, the signals T in the continuous time become EAT, in the discrete time become EAK. In the transformer you have the Laplace S, Laplace of the S. In the Z domain you can write the Z EZ. That means you take the Z transform of signal E in the Z domain. You take the Laplace of the E in the S domain. Laplace the transfer function will become integration 0 to infinity EAT E minus SAT DAT. In the Z domain definition will be K, that the integration become the sum K 0 to infinity EAK Z minus K. Okay, now we will see the EAT. If I take the sample become E star T. Careful, E star T all the time keep I take the sample about the EAT. If my signal is the black line is EAT, I take the sample of my signals become E star T. Or E star T, I can write the E sample of K. These two definitions that I will repeat a lot, every verse you must keep in the mind. EAT, I take the sample, I can write the E star T, or I can write the E sample of the K. What's the link between the Laplace star and the Z transform? E star, if you remember, I take the sample of the EAT. Sample of the EAT, that means such as a com of the, or the sum of the K equal to 0 to infinity A KTS sample Dirac T minus KTS. Impulse hold, I know that Z, if I put the Z is equal to ESAT, the definition of here I can change the Laplace of the E star S will be Z of the ESATS. This will be proved together.